All right, so we have a really good model for how hydrogen behaves, okay? We have a really good model for how hydrogen behaves, and we can predict the spectral colors for hydrogen really well. We can, to a great deal of precision, predict what kind of electron jumps are possible for hydrogen. We can predict what colors lights will come out, all that kind of stuff, okay? But as soon as we start to try and go any further, even to helium, okay, just one more proton, we start to run into a lot of problems. And what happens is that the Bohr model that we came up with, that nice equation that describes the energy of the atoms for a hydrogen, becomes more and more divorced from reality, becomes more and more greater and greater error in the calculations when you try and use atoms that have more electrons and more protons. Okay? And so that became apparent real quick. But the incredible accuracy of the Bohr model really led a lot of people to start to think, okay, there is some fundamentally really good stuff happening here. This, because we can predict hydrogen so well, there's got to be some additional complexity to these additional atoms that are larger, that have more protons, more electrons. That is, we need to be able to take into account. And so there's a lot of people who work on this. Schrodinger, Bohr continues to work on this. Heisenberg, a lot of guys spend quite a bit of time thinking and doing math to try and come up with a more generic solution, a way that they can explain not just for the nice simple hydrogen, but for the much more complex elements as well. Okay? And the model that they came up with is what we call quantum mechanics. QM, quantum mechanics for short. Okay? So, quantum mechanics is sort of the best model we currently have. We're not going to apply it in all its brilliant glory because the math required to do that is way beyond us. Okay? It takes calculus, fairly high-level calculus, to be able to do this kind of stuff. So we can't really apply the model to its fullest extent. But we can use the results of a lot of that modeling stuff to help inform how we view the electrons in an atom, the way that the electrons are arranged. And remember, that's what everything is all about. How the atom behaves chemically, how it bonds with other things. All that stuff is determined by the way that the electrons are arranged. So the more accurately we can explain that, the more accurately we can predict how the atoms will behave, which is one of the big things we want to do in chemistry. So, we have talked about fundamental ideas. We've talked about waves versus particles. And we've talked about light as a wave or a particle. We've talked about Einstein's work on trying to merge or come up with these two distinct views and trying to merge them together. Okay? So Einstein comes up with this idea that energy has mass and mass is energy. That these two things are really different expressions of the same fundamental stuff, whatever that happens to be. But we just experience it in two very different ways. Okay? Now, if you take these sorts of ideas and we start to think, how does energy function versus how does matter function? We see some interesting things that are the same and things that are different. Okay? So for instance, we know that light can be thought of as being continuous. That is that the light, we have these nice continuous waves. That's one way, a very successful way to think about this kind of stuff. We can also talk about matter appearing to be continuous, right? We talk about matter, initially you think, well, I can divide it in half and divide it in half and divide it in half. But we really quickly came to the idea that, hey, you know what? Atomic theory says that matter has to be made up of particles. That the only way you can explain things like the various rules that we talked about, Lavoisier, with a rule of multiple definite proportions and the law of multiple proportions, and we came to Dalton's laws that explain how matter behaves as a particle. And that was significantly more successful than matter looking like it was continuous. So if that's true, and we say that there's this equality between matter and energy, then does it not also therefore hold that light might have particle-type characteristics? And Einstein's work on the photoelectric effect and others researching that type of thing says, yeah, there are certain instances in which we have to look at light as if it was a particle, okay? Because that's the only way that you can realistically describe, model mathematically how it's behaving. It has to be thought of and calculated as a particle. Okay, but we have other things that say that light has wave characteristics. The only way we can explain diffraction and things like that for light is if there are these wave characteristics. So clearly, there is both. There has to be both particulate and wave type properties for light. That's the only way we can explain what's going on. Now, if we think about this great symmetry between matter and energy, if we've come to the conclusion that light has to have particle and wave characteristics, why then should not matter also have wave type properties? Can we model matter, can we model atoms and electrons as a wave, as having wave characteristics, having frequencies, having wavelengths, behaving in those ways? Okay? And it turns out that that kind of modeling is exactly what we need to explain how electrons behave inside of atoms. And that if you start to look at the calculations, the reason why we don't experience or see these wave properties in our sort of everyday lives is because the wave properties depend very heavily on the mass of the particles. The mass of the particle, the more massive it is, the smaller its wavelength will be. The smaller its frequency, the higher its frequency will be. So large particles like a baseball, for instance, behave, the wavelength, the wave characteristics are so small, they're undetectable by us. Okay? So large particles, the wave characteristics are just really, really small. But for small particles, like the size of an electron or the size of an individual atom, the wave characteristics take on really important significance. The way that the electron interacts with a proton is dominated by its wave properties, by the way it behaves as a wave. The nature, just like we talked about light as having wave characteristics about how it bends or diffracts, that's why we can see the colors, and that it has particle properties, that's the way it can knock electrons off in the way that it does. Matter has the same thing. And if we start to think about matter as electrons as waves, then we can actually begin to model much more complex situations accurately. Okay? Now, when we say a wave, we need to sort of think a little bit about what do we mean, what are we talking about here when we say wave characteristics. And it's complex in terms of the only real way to understand what we're talking about. There's no way to visualize it because there's nothing similar in your everyday experience that is in any way comparable to what we're talking about. So typically, it's the math that proves and shows how these things work. But we can't do the math. So we have to come up with some analogies, some sort of, well, how do waves behave analogies that we can apply to the way an electron might behave inside of an atom.
Could this be any way related to a sound wave?
So sound waves are waves, and the way that they behave is very similar to the way that all waves behave and the way that electrons behave. But when we talk about the way that an electron behaves as a wave, it's very different than the way a sound wave behaves as a wave. The math underlying the two, the math that we can use to describe them, is the same. But the physical representation is much more difficult to tease out. Because electrons don't behave like a sound wave in terms of compression and expansion of a gas. They behave like a wave in terms of their fundamental properties like position and velocity and those kinds of things. Okay? But the key to all of this is that waves have certain characteristics, and the math that we use to describe them leads to certain results. Okay? And one of the important facts about these sort of waves is the fact that we have what we call boundary conditions on the waves. Okay? And it's these boundary conditions that are what really are going to go through and allow us to come up with some sort of physical representations of an electron. And it's the fact that the waves have limits, and in a sense mathematical limits on how they behave, that lead to certain properties that we can express. Okay? So, what I'd like to do is I'd like to just real quickly show you some wave behavior. Okay? And this is probably stuff you may have seen before. So, I want to show you this, this really kind of nice demonstration of a wave. Here is a spring, an oscillator. Okay? And this spring, we can have it function like a wave. There's two different types of waves that we can generate with this spring. We can have a compression wave, which you can see moving back and forth there. But we can also have sort of a transverse wave, an oscillation. And this isn't going to work because that door is going to fly open on me. So I have to remember to pull it open like this, and flop that around. Okay, so here is a wave. It has a particular wavelength, which right now would be twice what this wave is, because a wavelength is a full up and down cycle. Okay, now this wave has a particular wavelength because it is bounded. There are certain points that are fixed. Each end of the spring is fixed. I have the far end that's attached to the door, and I'm holding in my hand the near end. So where I'm putting some energy in by wiggling it. But the wave drops to zero. Its amplitude, how high the wave is, high or low the wave is, drops to zero at each end. Those are the boundary conditions on this wave. These are what we call nodes. Okay? So a node is a point where the amplitude drops to zero. Now, you can see that I have a particular wavelength. I can have some multiple of this half wavelength inside this wave. Okay? Now, the distance here represents one complete wave. How many nodes are there? 3 nodes. Okay, I have a node on each end. Those are fixed nodes. And I have that node in the middle where essentially the spring does not move up or down. Now, the wavelengths that are possible are constrained or fixed based on these endpoints. I can't generate any kind of shape I want. If I try and generate some weird, non-integral measure of the half wavelength, if I try and do something that is like 0.2 of a wave, what happens is the wave is not stable and I just get random wiggliness. Okay? It won't establish a standing or steady wave. I can only get those at multiples of the half wavelength. Okay? So here is 2 half wavelengths, or 1 whole. I can get, okay, there's 3 half wavelengths, or 1.5. I can probably get to 4. But again, see, it's really hard to, anything in between, you get this crazy wiggle, right? All right. It's hard to do because I got to drive at a very high frequency to get the wave to be stable. Questions?
Can these waves move like instead of just the 2 axes, can they move like that?
Right. So I could have 3 axes. Right. This is actually a one-dimensional wave. This is a one-dimensional oscillator. I'll show you some pictures of 2-dimensional oscillators in a sec. Yeah, but fundamentally the spring is stuck in 1 dimension because it's basically aligned. This is still the same sort of wave. It's moving up and down. Fundamentally, mathematically, it's really just moving up and down. So we'll look at a two-dimensional wave. A drum head is a really good example, or a trampoline is a really good example of a two-dimensional oscillator. Okay? Electrons mathematically function as three-dimensional oscillators. They oscillate, they are waves in 3 dimensions. Okay? Matter waves, if you want to think about it that way. But really, what we end up mathematically coming up with is probability waves.
What about compression waves?
Yeah, sorry, say it again?
What about compression?
Compression waves, fundamentally the same thing. You have particles oscillating back and forth. You have nodes, yep. For standing compression waves, you get nodes, yeah, absolutely.
You say that you can only get stable if we use at what?
You can only get stable, what we call standing waves, at integer multiples of half of the wavelength. Right? So I can have, this is 2 halves or 1 whole, and we saw the full, this is the half wavelength. 1 up, 1 down as a full wavelength. I can only build multiples of this half wavelengths. So I can't have, 0.3 of a wavelength. I can't do that. I can get 1.5. I can get, 2 waves. I can get, 2.5. But I can't get any wavelength I want. You can only have certain standing wavelengths, certain integer multiples of half wavelength intervals. So I can have a half, 1, 1.5, 2, 2.5, 3, but I can't go off those points. Those are the only points where I can build a standing wave, where the length of the half wavelength, that length is determined by my constraints. It's determined by where is it fixed. Where are those boundary conditions? Where is the spring stuck? Okay? So in an atom, we have a certain set of boundary conditions that constrain the electron wave. It is the nature of this type of waves that the boundary conditions cause quantization. The boundary conditions cause the waves to happen in these integer multiples. Okay? So because of the nature of the boundary conditions, that's what drives the hydrogen atom to only have certain energy levels. The electron has to fit, okay, one way to visualize this is that the electron has to fit around, its wavelength has to fit around the atom. That's sort of a visualization. It's not really great mathematically, but it's not a bad visualization for what has to happen.
So is that like you're saying that the distance between
Where that point and this point is, that I have to have some multiple of that. Okay, that's the fundamental because that's where the boundary conditions are. In an atom, I have different boundary conditions depending on the number of protons, the number of electrons, and things like that. And that's what drives the quantization of the energy level. So we can think about this sort of boundary conditions. We can think about these waves and their oscillations in different ways. So what we saw, what we had here was a one-dimensional oscillator. Okay, that was the spring. It's essentially a line that we can cause to wiggle up and down. A two-dimensional oscillator would be a drum head. Okay, so a drum head has a certain shape and a certain way that it will vibrate up and down depending on how we hit it. Okay, so if you imagine your drum head and I strike it in the middle, bang, I strike it in the middle, the whole drum head can move up and down. Okay, I can get this up and down half wavelength. The boundary condition is the outside rim where the drum head is attached to the frame of the drum. Okay, now you can imagine a situation where I'm not just hitting it bang, bang real slow, but if I start to hit it faster, just like I started to shake the spring faster, I get another node forming. Okay? And this node is in the shape of a circle, so we call it a radial node. The radial node forms when you drive or shake or hit the drum head at a higher frequency. Now this is stable and this is stable, but in between, It's unstable. The drum won't stay in the... These are the what we call the standing waves that we can build. These are the natural wavelengths that we can maintain by oscillating, just like I could get certain wavelengths to work with the spring. There are certain wavelengths I can get with the drum. If I drive it faster, I'll develop more nodes. And so notice what's happening here is I've got this radial node, the point where the drum head basically doesn't move. And I have positive and negative parts of that. So parts where the amplitude is up and parts where the amplitude is down. We call those phases, positive and negative phase.
So for this thing, there would be 4 fixed points, but how?
So this is a fixed line, essentially, a fixed circle. The one-dimensional oscillator had points, right? This was one-dimensional, so it had points that were its fixed. In a two-dimensional, you have lines that represent the nodes, the fixed points. And so a three-dimensional oscillator, a three-dimensional system, would have surfaces, nodal surfaces, right? Two-dimensional sheets that would represent places where the amplitude drops to 0.
Sorry, it's just really creepy. Is that like when you drop a pebble and like
Yeah,
water
this is exactly, that's the ripples that you see like that. Now imagine you keep dropping pebbles. And what happens is those rings, they'll hit the edges and bounce back in. If you're dropping them at the right frequency, you're dropping the pebbles at the right way, the waves will interfere with each other and you'll get larger and larger standing waves.
and they come back because they hit the
Because they hit the side and they bounce in. Yeah, because they can't go out outside this fixed node here because of the way the system is designed. It's different, a little bit different in an atom, but fundamentally the same mathematics and the same concepts.
When they come back, would it be like the opposite of it, positive, negative,
Yeah,
negative,
well,
positive?
no, depending on how you drive it, it's the exact same. So it hits here and it bounces back, negative, positive, so that they add together what we call constructive interference. So that they build stronger and stronger.
But could it
If it came back the opposite way, the positive and negatives would cancel out and the whole thing would remain flat. Yeah. So that's destructive interference. Okay? So, radial nodes, okay, these are circles, the radial nodes that develop as we increase the frequency with which we're driving the drum to form. Now, in addition to the radial nodes, we can also have what we call angular nodes. Okay? And angular nodes, let's see if I can, yeah, that'll fit better. Angular nodes are if I strike the drum off center. So like if you imagine I have a drum head or a trampoline and I bang the drum on half of it, that half goes down while the other half goes up. And then the oscillation occurs like this. And I have a node down the middle. This is an angular node down the middle with the drum oscillating back and forth like this. And if I drive it with greater frequency, I'll get more angular nodes. Okay? And they'll cross. So these two will be down and these two are up and they'll oscillate like that. Okay? The drum, you have to imagine this is sort of vibrating back and forth with parts of the drum going up while the parts are going down. Up and down are only important in so much as they're opposite from each other. And if you imagine like the water wave, up and down are important only when they combine together to cancel out or two ups combine together to increase, they add together to give greater amplitude. What's going to happen here is that we're going to take this idea, this math explains what's happening in an atom really well. Okay? And so what we have is what we call the Copenhagen interpretation. Because it was developed in Denmark by Bohr and Schrödinger. So Schrödinger and Bohr working together up until about World War II when German Schrödinger had to go back and Danish Jewish Bohr had to stay in Denmark. A lot of interesting political stuff, World War II, a bunch of stuff. And the two of them basically never talked again because of all that kind of stuff. But together, they really did come up with the fundamental visualization and mathematics behind what we think of as the atom. Okay? And how we explain what's going on. And then the interpretation here is that the mathematics that allow us to describe the atom give us certain information. They can tell us the position of the electron in the atom, they can tell us the velocity, but there's a fundamental relationship between those two values that turns out to be probabilistic. That is, when we think of throwing a baseball, I can track exactly where that baseball is and how fast it's going the whole time. I have some really good math that will tell me with great precision how that baseball is going to behave from the instant it's thrown until it lands back on the ground. Okay? When you start to look at atoms, that kind of deterministic system no longer functions. That at those small scales, the wave nature of the electrons and the wave nature of the atoms mean that you can't predict exactly how it's moving. You can't predict exactly where it is. That there's a fundamental limit between those two things. And all we can really talk about is the probability of finding the electron and the probability of where it's going to be. We can only talk about things probabilistically. And a lot of that work is summed up in a very simple equation called the Heisenberg uncertainty principle. Okay? So the Heisenberg uncertainty principle fundamentally sets a limit on how well we can know the uncertainty in the position, so the delta uncertainty in x, the position of a particle, times the delta, the uncertainty in the momentum, velocity of the particle, is given this fundamental limit. The smallest it can be, it has to be at least as big as Planck's constant divided by 4 pi. Okay? What's important here for you, you don't need to, we're not going to use this. What's important for you is to understand that the way that we fundamentally model how electrons behave is by looking and thinking about them probabilistically. That there is this math that we use to describe things in terms of the likelihood of finding them, the likelihood, the percent chance of knowing where they are.
So if you know, like,
Position, where it is.
so if you know one more accurately, then it decreases how accurate
Right.
you know the other one.
Exactly. So the more accurately you know the position, the less accurately you know where it's going. The more accurately you know where it's going, the less accurately you know where it is. Uncertainty is basically the, usually we express it in terms of a plus minus value. So you could say, I know that its velocity is, 10 plus or minus 0.5. That's typically how we express uncertainties, although there are other ways.
So it's the probability of what?
Probability of finding the electron at a certain energy level or a certain place in the atom. That's fundamentally what this tells us, what the math will go ahead and tell us. And what we're interested in is how we can use that to explain energy levels in more complex atoms. Question?
What's delta?
Delta is change in or uncertainty in.
Like when you do y equals mx plus b.
Y equals mx plus b, yeah. And you have the delta y, that's the change in. Okay? So, what's tricky about a lot of this is that while we want to be able to predict this stuff, while we want to be able to predict these colors, the math behind this is well beyond the stuff that you're going to be able to do in this class. You need a more advanced calculus in college and stuff like that. But what I'm going to show you is the results of some of that math that we can understand, that we can interpret. And the math we're talking about looks like this crazy stuff here. This is Erwin Schrödinger, the guy who came up with what we call the wave function. Okay, and this symbol right here is a function. It does not represent a single number. It represents a whole series of mathematical calculations that represent everything about a particle. Doing the appropriate math to the wave function will allow you to get a probabilistic answer to where it is, how much energy it has, everything you want to everything you can, not want to, but can possibly know about it. Okay?
What's H?
So the H with this little caret on top is called the Hamiltonian, and it's some more functions stuff. And E is the energy. I'm going to wave my hand at this because there's no convenient way I can explain to you how this behaves without you knowing a lot of calculus. Even then, you have to know things like eigenvectors and eigenvalues and this whole branch of mathematics that you haven't even conceived of yet. Okay? So trust me, it's crazy stuff invented by variously Newton or Leibniz, depending on various historical debates. But it's incredibly useful for describing the world around us. I'm going to show you the results of some of this stuff that we're going to use in a pretty clean, pretty straightforward way to be able to predict, to be able to write down how are the electrons arranged inside an atom. What energies do the electrons have? Because that's what we need to know. Okay? All right. That's all for today. I wanted to give you this background so you could understand a little bit more of the history. It's possible that these kind of questions come up a little bit, but